Uh, at the last part of the last day's class, I saw there was a question which I did not have time to answer before the end of the class. So let us start with that. If I recall correctly, the question was that uh, if you put two electrons in a well, that could be any kind of well, won't they, since they individually are fermions, and if you have put two of them, won't they form a boson? No, they won't. The reason is that uh, if you have just two particles and nothing else in that well, then the two particle system does not interact with anything. And if something does not interact with anything else, there is no calling something a boson or a fermion. So a boson or a fermion, those characters manifest only when a particle is in company of other particles. So by itself, it will not. But then, when you put a large number of protons, neutrons, electrons together to form an atom, if the total number of fermions in that is an even number, then it develops characters of a boson, because these quantities, these fermions are actually tightly bound. They interact with each other much more intensely than they do with other particles in the neighborhood. And so that atom by itself can be called a system with various particles inside it interacting with each other much more intensely than they do with other particles. So in that case, that collection of particles will behave with the other particles like the way the bosons do. So just a particle being a boson or a fermion does not carry any sense. Particles do manifest their boson or fermionic character only when in company with other particles, that is manifested in their collective behavior. So is it clear? That was the question in the last class. So I decided to clarify that before proceeding further. So in the last class, we learned that the character, the overall character of a boson or a fermion, if I write them down, where is it? Yeah. If I write them down, the total wave function, total means including the spatial part as well as the spin part. Describing any system of identical bosons is symmetric with respect to particle exchange. Similarly, if you replace this by fermion, it will be antisymmetric. Okay, so I'm not again writing it, but you can of course write it. So the question actually pertains to total wave function, and total wave function has a spatial part, which we have seen that can be written in two possible ways. One is symmetric, another is antisymmetric, and the spin part, which can be written in four possible ways, three of them symmetric, one of them antisymmetric. And as a result of that, we have seen that there are four ways that a pair of fermions can live together. One was minus x1 comma x2. This was the antisymmetric one, and with 1 comma 1, this is the S, this is the MS part. That was a symmetric, so antisymmetric times asymmetric gives antisymmetric one. So that can be explicitly written as 1 by root 2 psi n x1 psi k x2 minus, because it is minus here, minus psi k x1 psi n x2. So this is the spatial part that's done, and this one S is equal to 1, ms is equal to 1 is representative of the up state in the z direction. Okay, up means first one is up, second one is up. Similarly, we can have the same composed with the other symmetric spin state, where this one is 1, this one is 0. This I'm not writing, and this one will be the same thing. So this, and here it will be up, down, plus down, up. Okay. This will also carry a 1 by root 2. So here it will be half. 1 by root 2, 1 by root 2, it will be half. And this part is the spatial part, and this part is the spin part. It's also possible to be in the third spin state along with the antisymmetric spatial eigenfunction. It will be 1 comma minus 1 then. This will be again 1 by root 2. This thing remains the same. And here it is just down. And these are the three possibilities where the spatial part is antisymmetric and the spin part is symmetric. So the total is antisymmetric. Or there's another possibility where the spin part is antisymmetric, the spatial part is symmetric. So it will be psi plus x1 comma x2. And the spin part is the singlet state 0, 0, which will be again 1 by root 2 comes from here, and another 1 by root 2 will come from there. So I'll write half here. And this is this plus this, which is the plus one. And this one will be up, down, minus, down, up. So these are the four states in which two fermions can live together, because this character is imposed by the condition that they are indistinguishable particles. Had they been distinguishable, then nothing of this sort would be there. And similarly, in case of bosons also, since the total wave function should be symmetric, there are a few ways you can get symmetric wave function. If both parts, the spatial part is symmetric, the spin part is symmetric, then you get a symmetric wave function, or both are anti-symmetric, then you get a symmetric total state. So you can see that then that because of the condition imposed by indistinguishability, particles are restricted to be in states. They cannot be in any other state because they are not distinguishable from one another. Now, this has profound implications. One implication I would show right now. So, do I need to really write down all the possible states for the boson? I have just written it for the fermion. So, these are the possible states for the fermion. And similarly, there would be possible 4 states for bosons in which bosons can be. Okay. earlier, when we were dealing with distinguishable particles, we have seen, I'll just draw a line here. We have seen that in the configuration space, in the x1, x2 space, there are two possibilities. If the first particle is in the ground state and the second particle is in the first excited state, we have already seen this. Now I will draw only the contour plot. When I explained it, I sort of drew things in like the mountains. So basically, we are plotting the mod psi square. Psi means it is composed of both the particles. So this side is our x1. This side is our x1 and this is x2. x1, x2. Now, depending on which particle is in the ground state and which particle in the first excited state, there are two possibilities. Suppose that the first particle is in the ground state and the second particle in the first excited state, we have seen, then there will be two peaks and there will be these equiprobability lines. Right? And if the first particle is in the first excited state and the second particle in the ground state, it will be in the horizontal direction. It will be like this. This is what we have seen. I'm just drawing in order to recapitulate what was the character for distinguishable particles. So have you understood what is the meaning of these contour plots? These are the plots. Actually, these are two mountains actually looking like this. And these are the equal probability part. So this is actually what we are drawing is mod psi x1 comma x2 square. This is what we are plotting, and that will have two peaks because there are two possible places where the first particle can maximally have the maximum probability of occurring, while the second particle in this case is in the ground state, so its wave function would look something like this, whereas this wave function would something like this. So this fellow has maximum probability of occurring here and here, while this fellow has a maximum probability of occurring here. And so you had these equiprobability plots. Contours are the lines of same probability. That is what we saw for the distinguishable particles. But none of these are really symmetric or anti-symmetric, because symmetry would be symmetry with respect to the x1 equal to x2 line, right? So what will effectively happen for indistinguishable particles? I'll again this. Here we are plotting only the spatial part. So you have seen that the spatial symmetric or anti-symmetric, and the symmetric part or anti-symmetric part will actually concern this 45-degree line or x1 equal to x2 line, and there are two ways of this happening, one symmetric, another anti-symmetric. So our x1 is here, x2 is here, x1 is here, x2 is here. A symmetric thing would mean that uh, uh, against exchange they would behave in the same way. That means their behavior will remain the same. Effectively, for symmetric ones, uh, the two peaks will occur on the 45-degree line, and the contours will be like this. While antisymmetric would mean that their peaks will occur like this, and their equiprobability lines or the contours will look like this. This is profoundly different. These are profoundly different from what you saw for distinguishable particles. So this is for indistinguishable particles. What does that physically mean? It physically means that uh, if there are a number of particles in some kind of a situation where then I'm not considering there is any force between them, because we have not considered in the v function any v of x1 minus x2. So we did not consider anything like this. So we did not consider any interaction. So this is, we have not considered. And yet we find that the particles that are in symmetric state will actually be distributed this way. They will have a larger probability of occurring along the 45-degree line, x1 equal to x2 line, and that is how they will occur. And in case of the antisymmetric spatial wave function, they will be occurring this way. That means they will be having different values, and there will be nothing, no probability of occurring on this 45-degree line. What does it mean? It means that we have already seen that if they are bosons, then by the way, it's not that these situation or this situation refer to bosons or fermions. It can be for both, because it actually depends on which state the spin are. If the spin are symmetric, that means up, up, or something like that. There are the four possible symmetric states. There are then a boson will be in this state. A fermion will be in this state. So if the spin are symmetric, the fermion will be in this state and the boson will be in this state. Now, what does it physically mean? It means that the bosons will sort of tend to have, the probability distribution will be such that the bosons will tend to be crowding around the x1 equal to x2 line. They will have a larger probability of having x1 equal to x2, which means the particles will be sort of crowding together, even though there is no force acting between them. This is a completely quantum mechanical effect, which has no analog in classical physics, where because of the indistinguishability that demand, what will happen is that some particles will sort of tend to come closer to each other. If the spatial wave function is defined by an antisymmetric wave function, they will sort of tend to go away from each other. They cannot be together. They will be away from each other physically. I mean, it is as if some kind of a repulsive force is acting between them, though actually there is no repulsive force. This is again a very quantum mechanical phenomenon, which has no analog. in classical physics. Now, as I said, that it is not true that this represents a boson, this represents a fermion, because that depends on their uh, both can be in both the states. But there are three possible ways in which the spin state can be a symmetric one. And if the spin state is symmetric one, the spatial state has to be symmetric for a boson, for a collection of bosons. So the bosons will tend to normally have a situation like this. They will sort of come close to each other. Uh, they will not come close to each other. And the fermions will sort of tend to go away from each other. But again, remember that these are not, you don't do not should not have a fixed idea that the boson will be like this and fermions will be like that, because they actually depend also on their spin states. But we can state, okay, by the way, we can also state the bonds rule. When you consider both the particles, then the bonds will have the form will be uh, for identical particles. Uh, this is that the probability of finding one particle in a small interval uh, delta x1 centered on x1 and another particle. We are not, earlier when we were discussing distinguishable particles, we specified the first one and the second one. Now we cannot do that. And another particle in a small interval delta x2 centered on x2 uh, is, now this will be the mod square mod psi. It can be either plus or minus, so I'll write plus minus here, uh, plus or minus. So x1 comma x2 comma t mod square delta x1 delta x2. So notice that there is a place x1, there is a place x2, and you define a small range around it, you define a small range around it, so effectively you define a box, and the probability of finding the particle in that box is given by this. And in case of the antisymmetric particle, uh, pair of particles, this probability will be 0, and in case of a symmetric symmetric a pair of particles with symmetric wave function will be oriented around this. Okay, so now this has a few very important implications. Let me get some space out there and we'll continue. This has very important implications. You can see that this immediately sort of leads to Pauli's exclusion principle, which says that which states that a fermion, two fermions can never be in the same state. So if one fermion is up in the z direction and the other fermion is also up in the z direction, then the spatial part uh, should have this n and k different, because you have seen that the spatial antisymmetric wave function was 1 by root 2 psi n x1 psi k x2 minus psi k x1 psi n x2. So if n is equal to k, the whole thing is identically 0. So it means that the 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 probability of finding the particle in that state is everywhere 0, which means if in addition to that you have the up up or down down position, so the same state in the spin, then k cannot be the same as n. So the spatial eigenfunctions, the spatial states of the two particles should be different. On the other hand, if say you are considering a particular combination of this, then that means particular n, particular k, and all that, then there are two possibilities. A spatial state will allow two possibilities of the spin state. So up up or down down, these possibilities are there. So those possibilities will be allowed, which means that if the spin states are the same, the spatial state must be different, and if the spatial state are the same, the spin state must be different. And since they're in any direction, say z direction, there are two possibilities, plus h cross by 2 or minus h cross by 2. Therefore, in a particular spatial state, only two particles can occur. One with upspin, another with downspin. No more. So this is the result of the Pauli's exclusion principle applicable to fermions. Such a exclusion rule does not apply to bosons, because boson can take any number of particles in the state because they are in symmetry. Let us see a few immediate implications of what we are learning regarding the many particles occurring in a system. Imagine that we have a metal, say iron, cube. With side L. Okay. Now, in this metal cube, the iron cube, what will be the status of electrons? As you know, the electrons in the outer shell will more or less be free, and they will move around inside this box, but they cannot go out. So they will move around inside this box and they cannot move out. And if they cannot move out, then it is effectively like an infinite square well. So there's billions of electrons in an infinite square well. A simple cube of iron or any metal will be effectively an infinite square well in which billions of electrons are there. Now, imagine the ground state of the electron. Now, the ground state, how many particles can be there? Only two. Out of a billion, only two can. Now, the first excited state, how many particles can be there? Again, only two. So, only two particles can be in the first excited state, and so on and so forth. Easily, you can see that billions of particles are there, and they are constrained to be in the excited state. They cannot all come to the ground state, or they cannot all come to the lower energy states. That is why in a chunk of iron, uh, electrons are there, but they are at different energy states, and they are constrained to be in different energy states. Only two can occupy one state. Now, imagine that you are sort of pushing it from all directions, trying to squeeze this box. What will happen? Now, each electron, we have learned in the last year that each electron has a energy. You've probably done it for a one-dimensional box, but the result for the three-dimensional box is quite similar. It will be a quantum number in the x direction, a quantum number in the y direction, a quantum number in the z direction. You only had this square when you learned 1D, y square h cross square divided by twice m L square. This is the energy of each electron. Okay. So if all the particles are in the ground state, all these are one. If a particle is in the ground state, all these are one. It is pi square a square by twice m square, and so on and so forth. So actually, one can have this one 1, these two 0. That's a specific state. This one 1, this two. This one 0, this one 1, this one 0, this another state. So a state means there are various possibilities, but I'm claiming that in each state, you can have only two particles. Now, suppose you want to squeeze it. Then what will happen? L will reduce. If L reduces, this whole quantity goes up. And that is true for each of the billions of particles. So for each particle, the energy level will go up. And that energy has to be supplied by the guy who is trying to push it. And it's practically impossible to push it. It's practically impossible to supply that amount of energy, because each particle will demand more energy because of the L squared term. Square means it is even more. That means if you squeeze it by a micron, then also the amount by which each particle's energy will be large, and that will have to be supplied for billions of electrons. So that is why metals are rigid. You cannot squeeze them. So explanation of this, mundane day-to-day things come from this kind of considerations. Not only that, astrophysics. For example, have you heard what happens when a star dies? When a star like the sun will die, it will take billions of years. You will die before that. Don't worry. So it's not that sun is going to die before us. Billions of years. But when it dies, there is a stage when it expands. The amount of hydrogen in its core, which is taking part in the fusion reaction, depletes, and as a result of that, the fusion reaction slows down, and at a critical moment, it cannot continue any further. So the core collapses by its own gravity, releasing a lot of potential energy, and that sort of pushes the envelope outside, and it becomes a very large star, but dim star, called a red giant star. And in the core of the red giant, further reactions start. For example, helium. If you add another 3 of the helium put together will fuse into something with 12 atomic number, and that you add another helium, it will lead to 16 atomic number oxygen. And so all these heavier atoms, nuclei, actually form inside the red giant stars, and at some point of time, even that stops and the star explodes. When the star explodes, the envelope is ejected away, but the core collapses. The core collapses into something called a white dwarf star. The question then comes, what makes the white dwarf star stable? For example, if you look at the star Sirius, that's the brightest star in the sky. Sirius is in Indian language called Lukthak, so it's easy to identify, especially in winter. If you look through a telescope, you see actually the Sirius is not one star; it's binary, two stars. One of them is a white dwarf. So white dwarfs are very common. What keeps a white dwarf stable? Now, in the white dwarf also, a similar situation occurs. There, the electrons run free inside the white dwarf star, and but they cannot go out. So effectively, there is an infinite square well of the size of a star. So the whole thing is in a single infinite square well harboring billions of electrons, and they cannot further squeeze. That means they resist any further squeezing effect of the gravity of the star. Gravity tries to squeeze it, but it cannot squeeze because it cannot supply this amount of energy to those billions and billions of electrons. And so that makes the star stable. And Chandrasekhar calculated that that also has a limit beyond a certain mass, about 1.44 of the solar mass. Even that will not be able to stop it. It will squeeze even, and ultimately the protons and electrons will fall on each other, forming only neutrons. So it becomes a neutron star. What keeps a neutron star stable? Again, the same phenomenon. The neutrons are unable to go out of the star, and effectively there will be it's exactly the same effect, but the particles concerned are neutrons. So in astrophysics, even this has a profound implication. After Satyendranath Bose conveyed his paper to Einstein, basically his argument was that there can be particles that are indistinguishable from each other, and thus there will be a special kind of statistics. When he conveyed that paper to Einstein, as you know, Einstein published it translated it into German and published it, and that's how we came to know, or we came to name bosons as bosons. But after a year, Einstein published another paper following the same lead, same argument, but he showed that there can be another. He conjectured at the time, calculated and conjectured that there can be another possible state of matter. What is that? Suppose you have a collection of bosons. Bosons means if they have the same spin orientation, they will tend to be in the first state that I showed. That means they will tend to sort of be in a state where x1 equal to x2. So they will sort of, in a strange way, they will be attracted to each other. They will try to condense. Now, if but they will not be able to come very, or should I say, they will not come very close to each other because they have thermal motion. If they have thermal motion, they will ultimately move away from each other. It will move in thermal motion. But if you cool them, then each particle has what is known as a de Broglie wave. Okay, that is inversely proportional. The wavelength of the de Broglie wave is inversely proportional to the momentum of the particle. So as you cool it, the momentum reduces. So the de Broglie wavelength increases. Now, suppose a situation is there when there are many particles in different places, and each one with a de Broglie wavelength that is small. So they will actually move around in their own thermal motion as a collection of particles. Let them be bosons; they will have a tendency to come close, but that does not mean that they will really be very close because they have thermal motion. But As you cool down, the de Broglie wavelengths, I'm just schematically drawing. So de Broglie wavelengths are like this, say something like this. So as you cool them down, they will come. There will be a particular density of the particles, and the de Broglie wavelength is increasing. So at some point, the density will be such that there will be multiple particles uh, within the length scale of the de Broglie wavelength. In that case, their individual wave functions will interact with each other and finally form a collective wave function. A single wave function describing the state of a large number of particles. And that has been named Bose-Einstein condensate. And that is a character of bosons, has to be bosons, otherwise this property will not be there, because you cannot have large number of particles with the same spin state condense unless they're bosons. He predicted it in early 1920s, and only in the 1990s we became able to test it experimentally, where people cool down rubidium atoms. That's exactly why I showed earlier that the rubidium atom would be a boson. So rubidium atom, they cool down to a temperature of less than 10 to the minus 7 of absolute zero, so that the de Broglie wavelengths are truly large, larger than the interparticle distance. And then they saw that yes, they're condensing. Another person did the same experiment, Ketterly probably his name. Uh, he did the same experiment with sodium, and he managed to create enough uh, size of uh, the Bose-Einstein condensate so that uh, they could divide them into two, and then he allowed them to interact with each other. If two wave functions interact, there will be interference. So there will be interference patterns, and he managed to picture that interference pattern, which actually established the fact that the Bose-Einstein condensate has actually formed. So, and after that, three of them got Nobel Prize for this experiment. So all these became understandable only when you consider identical particles, many particles together, and their collective behavior. Okay. Now, the way the whole entanglement thing happened was more of philosophical nature, because as you have seen that the traditional quantum mechanics that was developing at the time, now it has become traditional, but it was developing at the time, and there were two schools of thought. One school of thought, which is more prevalent today, called the Copenhagen interpretation, said that whenever you have a double slit experiment, a particular electron struck a particular point on the screen, just before it struck, it does not have a position. It actualized when it was observed. Now Einstein and many others, Schrodinger, Planck, and people like that, they could not accept this explanation, and they claimed that the quantum mechanics up to that time was incomplete. It needs to be completed. What is missing? What is missing is that piece of information that lets us know when a, say, uranium atom or nucleus will disintegrate. That additional piece of information that lets us know where exactly this particle is before it struck the screen and things like that. So they claim that it's incomplete, and in order to uh, to show the problems with the quantum mechanics that was developing at the time, the people who were at the thick of things, like Einstein and Schrodinger, they themselves thought experiments by which they try to demonstrate that it's not yet done. There's more to be done. I hope you have heard of Schrodinger's thought experiment, Schrodinger's cat. Let me delete this and so his thought experiment was that let that there be a box. Sorry, draw it better. Suppose there is a box, and in that box there is a cat. I hope without the whiskers, cats don't look like cats. So there is a cat here, and there is a contraption in which there is a bit of uranium, and when that uranium disintegrates, the alpha particle is emitted, then a Geiger counter sitting here clicks, and when it clicks, it triggers a poison that is kept somewhere here, a poison, and the poison gas kills the cat. And suppose it is now a enclosed box, you are not looking at it. So what will be the status of the system? So long as the status of this radioactive element is observed, it is in a superimposed state of having been disintegrated or being as it is. And then, so it is a superimposed state, you never know. And only when you open it, then you observe it, and then the state collapses. But then he argued that what happens to the cat if the radioactive element did not disintegrate? Then the cat will be alive, and if it did disintegrate, then there will be a Geiger counter will detect it. It will release the poisonous gas. The cat will be dead, and then only when you open the box you will know whether the cat is alive or dead. Till then, what is the state of the cat? Is it in the superimposed state of being alive and dead, or is it alive or dead? This is the Schrodinger's cat paradox. I would say that we do not yet have an answer to the question that Schrodinger asked way back, I suppose, in 1939. Sorry. But in 1935, Einstein, Podolsky, and Rosen posed another question. I'll come to that. They posed the question I'll just delete this. All these came from their claim that quantum mechanics is as yet incomplete. He posed the question that I will slightly reformulate, exactly not in the form that Einstein, Podolsky, and Rosen, EPR, wrote that paper. It was cast in a slightly different form by David Bohm, and I will state it in that form. Suppose a pair of particles are there here, and the pair of particles is in the singlet state. Singlet state means 1 by root 2 up down minus down up. In this state, you have prepared the pair of particles in that state, which is perfectly reasonable. We can always do that. And the pair of particles are prepared in this state, which means that the spin state of this particle and this particle, neither of these is really determinate. They could be up or down, but the total spin state of the whole particle is determinate, is this. Whole pair of particles is known, but each of these are not known. Now, after having created in this form, you allow one to move in this direction and allow the other to move in that direction and let them go far. One may be in Calcutta, another may be in Delhi. And then the guy sitting in Calcutta will makes a measurement of this one. So it reaches here and he makes a measurement of this one and with a Strangler-like apparatus and finds that it is up. Then immediately the other one is known to be in the down state. That means it is, if this is measured to be in the up state, this is immediately known to be the down state, which means that it was actually in this state so far, and suddenly the state collapses to only this, up, down, this one up, this one down. So how does it happen? It goes from this state to this state when I have made a measurement only in one place. So this total state was this. Instantly, the moment you have measurement, the total state becomes this. One of the two possibilities. One possibility was this one up, this one down, and second possibility was this one down, this one up. But out of that, one materializes, one actualizes, and the moment you made the measurement, the other one also takes a decision as to where it should be. How does it get to know that you have made a measurement here? That is a question that Einstein asked. Is it that the information of the measurement flew from here to here instantly, which is not allowed by the special theory of relativity? So how can this happen? But this is what is predicted to happen by the standard quantum mechanics. That was the question that Einstein posed. Well, the status of the situation is that initially the paper was written in 1935. After that, there was very little interest in that particular paper. Only in early 1950s, when David Bohm again revisited that, there was some interest in that paper. But over the last, say, 15-20 years, there has been a skyrocketing number of papers that cites the paper by Einstein, Podolsky, and Rosen. Why? Because now we know that this is something that actually happens. What Einstein saw as something that is a mysterious behavior, in his own words, spooky action at a distance. Now we know that that spooky action at a distance happens. A phenomenon that Schrödinger named as entanglement. He named it in German. Its English has come to be called entanglement. But this is something that we will take up in little more detail. Okay.
Sir?
Yeah.
Sir, this is out of a curiosity. So I read somewhere that there is another paradox called as the ER paradox, the Einstein-Rosen paradox, where like two distinct point is connected through a bridge, and that paradox is related to the EPR paradox. Sir, how they are related? Can you please tell?
I do not know about that ER paradox. Huh?
Okay.
EPR paradox is something that has ultimately led to the understanding of entanglement. So that's what I'm trying to talk about. I don't know about the ER paradox. I'll have to read up. I don't know. Okay. But
Okay, thank
effectively,
you.
the EPR paradox is one that sort of made a sea change of our understanding of this material world. Now we know that, yes, entanglement happens. And it is a non-local effect.
Yeah, like I was reading that the ER paradox gives rise to a phenomenon of the wormhole.
I would strongly advise you not to bother about wormholes and things like that at this stage. First, learn about the
Okay.
basics. Okay.
Okay, sir.
This is an effect that not a quantum effect. There's an effect coming from newspapers. They talk about these things a lot.
Yes, yes.
Do not be carried with that. First,
Okay, sir.
learn the basics, and from the basics, we slowly go into different understandings. Without learning the basics, you will learn the words. It will actually cause harm.
Yes, sir. Definitely. Thank you.
Yeah, let's end today. Huh?